describe first some flow visualization techniques which are quite simple and but at the same time very illustrative. So as all of you know, this flow visualization is very important, and in fact many of the early discoveries in fluid mechanics were due to flow visualization. In particular, Prandtl's boundary layer theory, he got all the intuition from flow visualization experiments. But one has to be very careful in interpreting the images, especially when the flow is unsteady, because you can get very wrong interpretations by just looking at the picture. And most of the methods basically involve introducing some sort of foreign object like a dye or a small particle, and this is like a tracer which is supposed to follow the flow. Of course, if you have a large particle, then obviously it won't follow. So it depends on the flow field as well as the particle size. And at the same time, whatever method you use should affect the flow as little as possible. And for those of you who haven't seen this book, I would recommend that you go through this. You can essentially learn fluid mechanics by going through this book. It's basically just a collection of flow visualization pictures collected by Professor Van Dyke from different sources, and it's put in a very orderly way, starting from low Reynolds number flows to supersonic flows. And this is so many of the pictures are from that book. So this is an example of smoke being issued out of a nozzle, and you can see that this is a jet which is coming out, and initially it is laminar, it becomes unstable with the formation of these vortices, and suddenly at this point you can see a lot of mixing, which is a characteristic of turbulent flow. That is, you suddenly get this disorderly motion, and you can see all the smoke is dispersed out. And an important concepts in flow visualization are knowing what these 4 lines mean: streamlines, pathlines, streak line, and timeline. And streamline is essentially a line on which at each instant in time the velocity is tangential to that line. And so you have all these path line is the path followed by some specific fluid particle. Streak line is all the points which have come out of a specified point. So one simple way to illustrate this is if you look at the smoke coming out of an agarbatti. That smoke which you see, what line does that represent? So it's a streak line because all the smoke has come from that burning point. But so if the flow is steady, if the smoke is going steadily upwards, then that straight line would be one of the streamlines. It would be a path line because all the particles follow that path. But if it happens to be unsteady, like if it is wavering around, then at all points in time, of course, this will be the streak line. But certainly, for example, if you take a point here at an instant t, and at a later time this point has gone there, so the streamline locally will be here. So you cannot see anything about the streamlines or the path lines just by looking at that smoke coming off from the agarbatti. And one of the common techniques, I just wanted to show this hydrogen bubble technique because it's kind of important, but it's not so useful for free convection flows because of the buoyancy of the bubbles itself. So basically it is electrolysis technique, and you produce hydrogen bubbles on one surface, and usually it's a wire. And in all these techniques, as I said, you should not change the flow field. So for example, the diameter of the wire itself should be small enough that the Reynolds number based on the diameter should be less than 40, because beyond that you start getting recirculation and things like that. So it will start affecting the flow itself. And of course there are all these specifications which you need to follow if you want to produce good bubbles. And you can pulse the wire and you can get a series of bubbles. So this is an example of a pulsed hydrogen bubble technique in a turbulent flow. So bubbles are released periodically. So there are two bubble lines are released in quick succession, and you see what happens to these bubble lines as they go forward, go downstream. And the point about interpreting the flow, you can see from here, the shape of this wrinkled line is essentially an integrated effect of what has happened from the start of generation of the bubbles till that point. So you cannot really say this flow is turbulent, because the turbulence, if it had existed only here, it would have wrinkled the line. But if the turbulence, for example, has died here, it will be non-turbulent flow, but still this wrinkled effect would exist because of what has happened in the history. So that's why one has to be careful in interpreting these various techniques. But what is more important for us in free convection flows is a similar electrolysis based technique, and you use pH sensitive dye here. Okay? And this is an excellent technique for low speed flows, because one of the important things, as I mentioned, is the tracer should follow the flow. So here, by the very nature of the generation itself, the dye which is produced is neutrally buoyant. So it becomes very important for free convection flows where the velocity itself is small. So typically, one uses either Thymol blue or fluorescein, and this technique is very nicely described in this paper by Baker in 1966. And clearly it cannot be used for velocities with greater than about 5 centimeters per second. So this is an example of Thymol blue technique used by Sparrow, Hussar, and Goldstein for Rayleigh Bernard convection, in fact. So this is one of the electrodes, that is the heated plate. So dye is produced there, and it follows the convective pattern so you can see these plumes which are formed on the plate. Okay? And this is at a higher Rayleigh number, you can see more number of plumes and more closely spaced plumes. So this technique is laser-induced fluorescence, which I'll talk about a little later. And another common technique is using particles in the flow and taking long exposure photographs. So typically this is again jet coming out of a nozzle, and you can see here these long streaks essentially represent both the direction of the flow, that is the streamlines, as well as in some sense gives you the velocity field. But here you can see this is the entrainment which is happening by the jet. It is capturing all this outside fluid and it gets into the jet. And so that outside ambient fluid, entrainment field, is being captured by this very simple technique. So Shadowgraph and Schlieren techniques are those which are based on changes in refractive index. Basically, if there is a gradient in refractive index, the light rays bend, and you use that to visualize the flow. And it's used in two types of flows. One is where you get refractive index gradient because of density change, and that density change can happen at when the speeds are very high, like high Mach number or compressible flows essentially. And the other type of flow where you get density change is, of course, pre-convective flows, where density is the driving force. And for example, for gases, the refractive index is directly linearly related to the density. And essentially what happens is you have a ray of light passing through the test section which has these refractive index gradient, and because of refraction, it deviates from its original path. And one important thing to remember about this deviation is that it's an integrated effect over the entire test section. So both Shadowgraph and Schlieren techniques gives you an integrated effect of what is happening through that ray, path which the ray follows. And this Lippmann and Roscoe Elements of Gas Dynamics is an excellent textbook which describes this both Shadowgraph and Schlieren techniques very well. And essentially this is what happens if you have a density gradient, the rays refract, for example, towards the regions where you have higher density. And Shadowgraph is particularly simple technique. So all you need is a near collimated source of light. So it can be just like a projector, for example. And what happens is if you consider two rays, for example, and one of them deviates to a larger extent than the other, then this place will show a lower intensity. And the contrast for Shadowgraph is basically related to the second derivative of the refractive index. So what that means is that you need large changes in density to be able to observe the flow field. But the main advantage, as I said, it's very simple, and a simple light source will do the trick. And for example, if you have a density field like this, then the first derivative is like this, and the final image which you see is one dark and one light band. And this is a picture of a bullet which has gone through the air, and because the bullet is at very high speed, it creates, due to compressibility, it creates refractive index changes. And you see this very fine structure due to the turbulence itself. And so it's an integrated effect. So all these small structures are in fact like the Kolmogorov scales, probably. The Schlieren technique is a little more complicated, and but it is more sensitive in that it is proportional to the first spatial derivative of the refractive index or density. And typically what you have is a slit source which passes through the test section, and then you image the test section onto a screen, and at the image of the source you put a knife edge. So the knife edge is an integral part of the classical Schlieren system, and basically depending on whether the light rays passing through a certain point deflect upwards or downwards, more or less of the light is blocked. So this is the knife edge. So if the light rays corresponding to that point, for example, deflect upwards, then on the screen corresponding to that point, it will become lighter. So because large lenses are expensive, typically Schlieren are used with reflective mirrors. And this is an example of a Schlieren picture of a shock wave. And you can see that, of course, in a shock wave you get very steep gradients in density, and then you can capture all these images quite well. And more recently, something called the background-oriented Schlieren, which is much more simple compared to the classical Schlieren technique, is you have some sort of ground glass, and you have the diffuser screen and the light source, and you just need a CCD camera to image. And because of the refractive index gradients, the original background image changes, and then the difference between that is again like a Schlieren image. So again, it's relatively simple compared to the original or the classical Schlieren technique. So I will next describe some of the optical techniques which are currently in use. So basically, laser Doppler velocimetry, which is for measuring velocity at a point, Then particle image velocimetry, which is much more recent and much more widely used currently. It gives you a field measurement, mostly in a plane. Then measurement of concentrations, and a little bit about thermal imaging. So the essential method of LDV is having two laser beams intersecting at a point. Of course, it won't be a point, it will be some very small volume. So basically that volume will be the one in which you will be measuring the velocity field or the velocity. So as I said, it's a point measurement in that you get the velocity information only at that point where the two laser beams intersect. And the way it works is you have tracer particles, very small particles in the flow, which scatters light, and you have some sort of detector which takes in that scattered light, and that scattered light signal is used to obtain the velocity information. So it's essentially non-invasive apart from the fact that you introduce particles, and it gives you a direct measure of the velocity itself. There's no calibration required, unlike in a hot wire anemometer where again it's a point measurement, but it suffers from the need to be calibrated often. And it can be used for turbulent flows. Basically, you can get high data rates, and you get good spatial resolution, which are important for measurement in turbulent flows. Of course, the limitation is that both the fluid and the wall needs to be transparent. And it is relatively expensive because of the laser and the optics itself, the analysis. But actually, if one has the motivation to build one, then it turns out to be relatively inexpensive, except for the laser, and the laser nowadays are quite cheap. So, but just the electronics itself is not that difficult to build. And one problem, of course, arises in this technique. If you go very close to the walls, then you have problems with reflection. So it is been used in widely for a number of applications, and it can be upgraded to PDPA, where apart from getting the velocity, you can get the size information. For example, if you are looking at multi-phase flow, which has particles or bubbles or whatever. So this is the basic components, and for a single component measurement, you have two laser beams. This shows the same thing, and one can have frequency changing, etc. if you want to measure velocities where the mean velocity itself is very close to zero. And the scattering is based on mean scattering, in that the particles are slightly larger than the wavelength of light, and the intensity itself goes up with the particle size. And but of course, there is a limitation on the size of the particle which you can use, because it has to follow the flow. And you get most intense scattering intensity in the forward direction, and least in the backward direction. And this is basically the theory behind the principle. That is, you have these particles which are crossing this measurement volume, and because of the velocity, you get a Doppler shifted frequency, and the shift will be slightly different in the two beams because they are at different angles. And the difference between these two results in a beat frequency, which is this, which is essentially related to the velocity of the particle itself, which is the velocity of the fluid at that point. So you get a direct measure of the velocity based on this Doppler frequency into the wavelength, and this basically is the angle between the two beams, which you can change by changing the optics. And as I said, if the in this form you cannot detect direction. So both, if it's moving forward or backward, it will give you the same velocity. To measure direction, what you need to do is in one of the beams you have a frequency shift, in which case you can get you can measure the velocity and direction, magnitude and direction, using this frequency shifted beam. So this is another interpretation of LDV, which is sort of more intuitive or more physical. So basically you have these coherent beams crossing each other, then you get this interference pattern because they are coherent, and essentially you get regions of high intensity and low intensity, and if a particle crosses this measurement volume, it will cross this fringe pattern as well, and each time it passes through a dark or bright region, the intensity itself will change. And clearly you can see if the particle is moving faster, then that frequency will also increase. And the other thing to notice, of course, is that it measures the velocity perpendicular to this fringe pattern. So if the velocity of the particle is something like this, what you measure is the one component which is perpendicular to the fringe pattern. So essentially the signal will be like this. Okay. And this frequency, this time period will give you the Doppler shifted frequency, and from that, of course, you get the velocity. And typically, if you want, for example, 3 components, you can use, for example, an argon ion laser which has 3 frequencies. Or nowadays, you get the solid state lasers which are much cheaper and much more robust. So basically, you can, using a 3D LDV system, using 3 different wavelengths, you can get the 3 components of velocity at a point. So I was mentioning about the Mie scattering. So you have the source here, and the receiver can be in any place. So if it is forward scattering LDV system, then you can put the receiving optics, for example, here or here. But the problem here is because of alignment. So for example, if you have a large test section, and then at all times when you move the volume, when you move the whole system around to measure the velocity at different points, the alignment has to be kept in place, which is not easy because these are quite bulky. So as a result, currently most of the LDV systems are backward scattering, where everything is in one place. That is both the laser and the detector. So you look at the backscattered light, but the only disadvantage is that it has much lower intensity. So you need much more sensitive sensors. But the biggest advantage is that you don't need to align the system each time. So nowadays you get very, very small LDV systems which you can just essentially carry around. And signal processing, as I mentioned, basically looking at this high frequency and obtaining the beat frequency. And since again electronics is so cheap now, you can, for example, in your GPS it can go to, I don't know, nanoseconds. Huh? So these frequencies are much more amenable to current day electronics. So essentially you have this original signal, you remove the pedestal, and then what you're left with is this. This is what you need to measure. And seeding particles can be like any part, many times whatever, for example, in this room, there's enough seeding particles that you don't need anything extra. But if you want consistent signal, then usually you need to seed it with either droplets or some sort of particles which are small enough. And for example, if it's a compressible flow where the flow goes through a shock wave, right, then if you want to follow the fluid, then the particle inertia should be small enough that it follows that sudden deceleration. Okay, this is just the frequency shifting which I talked about. And for multi-component, you need either 2 or 3 lasers. And of course, there are a number of applications, starting from small scales to large scales. For example, in wind tunnels. And this one shows the velocity measurements around a car model. And one can, in fact, take it underwater and do measurements inside water. So particle image velocimetry is again a very common technique. In fact, it is more common than LDV currently. And so what it involves is again a laser, and it's usually a double pulse laser. So it basically has 2 lasers within one, but the optics is all aligned. And the laser beam is converted to a laser sheet, light sheet, by having a cylindrical lens. So it expands only in one direction. So essentially you have illumination in one plane. And so this whole plane is illuminated, and that plane is captured in a camera. And again, you need seeding particles, which will basically again scatter light. And the technique is much more simpler than LDV in the sense that what you're essentially doing is getting the velocity of each particle in the flow field. And again, this is important to have tracer particles, especially in like free convection flows where the new particles need to be neutrally buoyant or at least very small such that they follow the fluid. And of course, again, like in LDV, it is non-intrusive, and it has been used from essentially whole range of flow velocities. And you can get 2 or 3 components of velocity simultaneously. And most of the PIV systems are like around 10 hertz. So that is, you get a velocity after every 1/10 of a second. And more recently, you get these time-resolved PIVs where you need to use high-speed lasers where the pulsing rate is much higher. But these are, of course, extremely expensive, and they frequently break down. And for low-speed flows, you don't need really a pulse laser because the speed is low enough. Then you can use a continuous wave, continuous wave laser and a high-speed camera. So just like in LDV, you need optically accessible test section. And one of the drawbacks is, of course, that you cannot simultaneously resolve both the large scales and the small scales. Even though the technique is simple, one has to do some sort of image processing and signal processing. This is in section. So 3D PIV are coming now. So then you illuminate a volume. Then you will need at least 3 cameras to get the flow field. And even there, the volumes are relatively small. Velocity, yes. So it depends on your camera. So something like 1000 by 1000 pixels. Then you need a interrogation window, and where you do the cross correlation and find out the velocity in that interrogation window. Only for the tracer particle, yes. And then, so there should be sufficient number of tracer particles that you get almost continuous field. It will be like your numerical technique. It will be getting at each grid point. Then you do some sort of interpolation to get the velocity field. Yes. No, not really. What is the, Shashikant, you know, what is the current, in your field, how much was it? So 150 in a 2D, this thing. Because it won't be equal to the number of pixels. So few pixels will become an interrogation window, and that will determine the size. So that's why it becomes hard to get both large scale and small scale. So supposing you want to resolve the Kolmogorov scales, then you need to zero in on a very small window. So the whole viewing window itself will be very small. Then you lose out on the large scale features. And similarly, temporarily, you cannot get high frequency information like LDV or hot wire, where you can go up to kilohertz easily. But here you are restricted to that high speed laser. If you use, then it will be, you know, like 100 hertz or 1000 hertz are, as I said, very expensive. Resolution is more, but you get a single point, I mean, that measurement volume. So those volumes can be very small. So it's spatially, it will be well resolved, spatially and temporally, because you get high speed data. So you get turbulent information at a point. So the advantage of PIV is that you have information in the whole plane simultaneously. But you don't get that type of resolution. So this is what is called planar laser induced fluorescence. So the technique is again similar in that you, from a laser beam, you create a sheet. And this has been there for a longer duration of time, but it is extremely nice way to visualize what is happening in a plane. And the technique works in the using a dye which is excited by the laser. So it's a fluorescence technique. And so basically you have laser light, for example, green light coming and falling in this test section. And the flow or the fluid is laced with a very small amount of fluorescein dye. And wherever the dye is present, you will get some fluorescence. And that is captured on your camera. So in fact, that picture which it was in so you need to use a fluorescent dye, and as I said, you get very high spatial resolution, which is limited by the pixel itself. And one of the limitations is, of course, it's optically accessible, it should be. But more important for convective flows. So you will have refractive index gradients. So because of refractive index gradients, the laser light will refract. So you won't get a uniform intensity light. So in fact, if you look at a sheet of light like this, because of refractive index fluctuations, you'll start seeing lines here, which are dark and bright lines, which if you want to measure, for example, the concentration, then obviously this will give you wrong information. So then what you have to do is match the refractive indices of the fluids. For example, if you are using the salt to create density gradient, but still maintain the density difference which is causing the flow. So refractive index should be matched, but the density should be different. So that becomes very complicated, and so to do that, so this is an example of fluorescence image taken in our lab by Shashikant. So here he had to measure the intensity, he had to put this refractive index matched fluid, as otherwise this image would have shown all those streaks. And so basically what happens is your light is going from left to right. It is, the intensity is proportional to the concentration of dye, which would be the concentration of the, for example, the denser fluid. But at the same time, as the light goes from here to here, it gets absorbed. So you have to take into account that absorption, which is given by this equation. So that correction has to be made. And besides that, you'll have some other changes in concentration due to the optics itself, and some noise from the camera itself. So basically one has to correct for all that. So what is done, what we did in our experiment was, in the background itself a small amount of dye was put, and in the fluid which was, we were trying to trace, a larger concentration of dye was put, and using these two concentrations we could eliminate those constants, and finally we can get the concentration of the flow field or the tracer, not the tracer, the heavier fluid, for example, measuring the intensity of the flow at that point. And of course, in this example, you can see that you get extremely sharp gradients. And these sharp gradients are because we are using salt water here, and so that has a certain diffusivity, and the fluorescein dye itself has a certain diffusivity, and the hope is that the diffusivity of these two are similar, and diffusivity of both salt and fluorescein is very, very small, and that's why you get these extremely large gradients in intensity. So the Prandtl number is very large here. So the viscous layers will be much thicker compared to the density gradients which you get. So that will be the Bachelor scale. So basically the Schmidt number for the dye itself is 10 power 4, and for the salt it's around 600. So just briefly about thermal imaging, which again is becoming more and more common. So for example, this shows the temperature field around the aircraft. And so you get a variety of different types of cameras. And typically something like this would be like 4-5 lakhs, which is reasonably good for most applications. But if you want much more accurate ones, those will be like 30-40 lakh rupees. And one important thing, to get the precise value of the temperature, you need to know the precise value of the emissivity itself, which is not easy to get. For example, if you get an image of this board, you'll get a certain thermal image. But to relate it to the temperature, you need to know precisely what the emissivity of that is. So recently we've been doing some experiments of drying of like soil, the porous media. And what we realized then is, so it was by infrared heating. So imagine some sand, wet sand kept in a bowl, and which is heated from above. So we are looking at evaporation from such sources. And so the infrared is heating the top surface like the sun, and we are imaging with the infrared camera. And what you see is the emission from the black body radiation of the soil itself because of its own temperature. But apart from that, you are seeing also the reflected IR light. So that is contaminating the signal. So essentially, these are glass beads for very small, like 0.1 mm glass beads, which is filled with water. So this is after some time. And you can see that here, this is without shielding. This is the temperature field which you get. That is, but the correct way to get the correct temperature field is by shielding of momentarily shielding of the IR source itself. So if you do that, then you can see there's a difference of about 6 degrees. And it is much more apparent here. These are stainless steel balls, again saturated with water. And this is the thermal image which you get without shielding. And after shielding, the image is very different. So we've done experiments with imaging the surface of the water which is convecting. So there, unfortunately, that movie is not playing, but you get these very nice plume structures. And so the important thing to remember is if there is some input infrared light, that has to be blocked to get the correct temperature field. And the other important thing is the getting the emissivity right. So you have any questions on these? Yeah. It is same, right? So it is a much simpler technique compared to the older Schlieren method. Yes. In fact, Shashik, if you have any more detailed questions, you can ask them. So we just used an overhead projector. And in fact, what I would suggest is people who are doing experiments not to throw away their overhead projectors because they are very useful for these types of things. Of course, now it's very hard to get them, but so basically, you'll have particles in the flow field, and so this field is broken up into squares, which are the interrogation windows, and each interrogation window will have several particles. And essentially, you take the cross correlation between these two intensity fields at first instant and next instant. And those peaks essentially will give you the velocity. So it's, I mean, in principle, one can follow each particle and get its velocity. But that of course is not possible since you have a large number of particles. So what you do is have these large number of particles and take the cross correlation between these two images, and you'll get a peak at that point where corresponding to the correct particle displacement, from which you will get the velocity field. And in fact, one can go back later and look at the individual particle displacements to get a finer velocity field or better velocity field in terms of the variation within that window itself. So there are a lot of techniques which are being used to get, smoothen out the data finally. Because if you want to get, for example, vorticity, then you need the gradient of velocity, and then how you obtain that gradient depends on all these fine things which you do in the processing. So each interrogation window will typically have about 32 by 32 pixels. And number of particles in the interrogation window will be on the average 10. So the question Mahendra was asking about, what is the resolution of the velocity itself? So it basically comes from average of like a few particles in that interrogation window, getting the velocity field in that window. So that will give you the spatial resolution essentially. But the important thing is, two important things which you need to keep in mind. If you have a range of velocities, then at the highest range it shouldn't go out of the window. But at the same time, at the lowest range, they should show some displacement. And the other important thing is out of plane motion. So you have a certain laser light thickness. So the particles should remain in that thickness when you go from one frame to the next one. Otherwise, you lose that particle. And in the case of 3D PIV, essentially what you have is a volume illumination, and then you have 3 cameras, and then use a similar method to get the velocity field. And in all this, of course, you get, like in CFD, you get tons of data. So finally, you have to see what you want to do with it. You have to ask the right questions. Talk about is examples of the different experimental techniques or results of using different experimental techniques. Mainly in Rayleigh Bernard Convection, where we have used, most of the visualization has been trying to visualize what is happening close to the wall. So basically it's visualization of the plumes for 2 different types of experiments. Both are in water, one with using heat, so where the Prandtl number is around 6, and the other is using salt to create the density difference, in which case the Prandtl number or the Schmidt number is of the order of 600. And like Stevens mentioned, of course, a lot of high Rayleigh number experiments have been going on using very special fluids like superfluid helium and compressed gas. And to get high Rayleigh numbers, most of the experiments are confined to aspect ratio equal to 1. And the other type of experiments which I will describe is what is called tube convection. It is convection in a very long vertical tube, and it's a relatively new type of flow. So it is like Rayleigh Bernard convection, it is again free convection or buoyancy-driven flow. But it is, in many senses, it's very different. And so you get much higher fluxes and much stronger turbulence, much higher Reynolds numbers compared to Rayleigh Bernard convection, much more easily. And in fact, you can achieve this ultimate regime quite easily in tube convection. And I'll also briefly talk about boundary layers, which Stevens also kept referring to, that is what happens close to the wall. And this is more my personal opinion rather than what is obtained in the literature. So you're all familiar with these 2 terms, Rayleigh number and Prandtl number or Schmidt number. If you use species instead of heat, then of course it is diffusion of the species, which is exactly equivalent to Prandtl number. Of course, the main thing to remember is that it goes like length scale to the power of 3 and directly proportional to the density difference. And again, this must be familiar to most of you. What happens as you increase Rayleigh number, so in Rayleigh Bernard convection, and for example, you keep the temperature difference same and you keep increasing the height. So if the temperature difference is so much and the distance between the plates is 3 mm, then the Rayleigh number is about 1500 and you get pure conduction. When you increase it to 5 mm, it becomes laminar convection where you get steady rolls. And at around 10 power 5, you start getting time dependent rolls and also some three-dimensionality. And finally at around maybe 10 power 7 or so, the convection becomes turbulent and you get essentially uniform temperature in the core and very steep gradients of temperature at the two walls. And Nusselt number essentially goes like Ra to the power of 1/3, and actually it's closer to 2/7, which means if it is exactly 1/3, the implication is that the heat flux is independent of the height. So it doesn't matter if it is 1 centimeter or 100 meters. If it is in that regime, the heat flux is constant. What that implies is everything is basically governed by what happens near the walls. And this is some sort of schematic of what happens in Rayleigh Bernard convection. You have these plumes and you have this bulk outer flow. And the Nusselt number is the non-dimensional heat transfer. And I wish to point out this near wall length scale, which I will again talk about a little later, which normally people don't use. But I feel if you want to describe near wall flows, this is the appropriate length scale to use. Just like in turbulent boundary layers, the length scale is the near wall scales, that is y plus and u plus. And there again you would use a velocity scale and a viscous length scale to non-dimensionalize the velocities and distances. So one type of experiment which I said is basically using salt. And so in this experiment what we did was we have salt water in the top tank, fresh water in the bottom tank, and you have a very fine membrane connecting the two. So what happens is, for example, if the membrane is fine enough, the pores are fine enough, the salt diffuses through that membrane and essentially you'll get a heavier fluid at the bottom. So it's exactly like what you would have on a heated plate. So you have a layer of unstable layer on next to a surface, and because it's unstable you get convection. So this is like Rayleigh Bernard convection, but using salt. And the advantage of salt is that you get high Prandtl numbers. So usually earlier when people tried to simulate high Prandtl number flows, what they did was increase the viscosity. But if you increase the viscosity, the Rayleigh number comes down. But here the advantage of using salt is the diffusivity is small, so the Rayleigh number goes up and the Prandtl number also goes up. So you get high Rayleigh number, high Prandtl number convection quite easily using salt water and fresh water to create the density difference. So as I said, this membrane is important. The pore size should be such that you get pure diffusion here. And we've done some experiment where the pore size is larger in which case you start getting a bulk flow across the membrane. So that is again an interesting type of flow, but it's not diffusion, so it's not quite Rayleigh Bernard convection. And then, so we put fluorescein dye in the bottom tank, and a sheet of laser light just above the surface. So what we have visualized is what is happening very close to the surface. So if you can imagine, this is the membrane surface, and then the laser sheet is just above that surface, and if these plumes are crossing that sheet, so what you see is those lines corresponding to those plumes. So what you see are typically lines like this, which correspond to the plumes which are rising from the surface. So as I said, the Prandtl number is around 600. The other technique is the standard technique or experimental setup where you use heat, and so basically you have a heated plate here. So you start with the insulation, and then if you want to measure the heat flux, one technique is basically to use something like a glass sheet and measure the temperature difference across that glass sheet. So from that, knowing the conductivity of the glass, you can get the heat flux itself. And of course, this is slightly different compared to regular Rayleigh Bernard convection in the sense that this is open to the atmosphere. So you have evaporation happening here, but still you get finally steady state convection here. So, and the advantage of course is that you can visualize what is happening close to the wall. And here we use the Thymol blue technique to visualize what is happening close to the wall. That is basically create the dye on the surface and see how that dye, once created, moves on the surface and moves away from the surface. So this is our examples of PLIF images, laser-induced fluorescence images, just above the membrane as I mentioned. And you get these variety of plume structures. So essentially each line corresponds to a sheet plume, and you're seeing a cross section of that. So each of these lines, you can imagine heat is, fluid is moving away from the wall, and if it's a heated wall, basically you'll get hot fluid along these lines, which is convecting upwards. So you can see that one of the important things I want to mention here is that there is a strong interaction between the outer flow and the flow next to the wall. And basically what you see here is the signature of that outer flow. So here you can see these plumes are sort of aligned in this direction, and here they are aligned in a different way. So essentially, if you look at the flow structure in this type of convection, it will be something like this. Okay, and in the plan view, you have these plumes which are sort of aligned in this direction. So essentially, the outer flow creates a signature on the near the wall in terms of how the plumes are aligned. So here, what is happening is the outer flow is impinging like this and going outwards. So similarly, here you have multiple impinging points, and here it's a single roll. So the flow is impinging, outer flow is impinging here, and then going around like that. So this is not aspect ratio 1 cell. So if it's aspect ratio 1 cell, you get typically a single roll. So that was using salt, and this is using heat and Thymol blue technique. This is again at different Rayleigh numbers, and if the Rayleigh number is small, then you get this typical cellular structure. So these are again the So if you remember, the Thymol blue technique essentially produces pH sensitive dye on the surface, and because of convection near the wall, the dye accumulates along these lines. Okay, so basically these lines represent again the base of the plumes. So basically you have these plumes and they will be continuously moving around. As you increase the Rayleigh number, the flow structure changes. So you can see from a nice cellular structure, here you have plumes which are sort of aligned in this direction, which again, as I mentioned earlier, is a signature of the outer flow. So the flow is impinging here, moving along the diagonal and rising like that. So, and as you keep increasing the Rayleigh number, this plume structure becomes more and more chaotic. And also you can see that the plumes become closer to each other. So this is the fluorescein dye picture. I'll show the movie later on. And you can see this very nice leaf-like structure here. So it's along this fluorescein dye lines where the buoyant fluid is rising. And what I was mentioning earlier is that this is the basic structure next to the wall, and it's equivalent to those of you who are familiar with turbulent boundary layers or turbulent pipe flow. The near wall structures are essentially the sublayer vortices. So for a long time people called that the laminar sublayer, but that is again a wrong terminology. It is actually a viscous sublayer and it is turbulent. So, so basically we looked at modeling of these plumes and the near wall scaling, and one of the papers here basically showed that the amount of heat transfer is related to the plume length. If you can measure the length of the total plumes here, then the heat transfer is basically related, total heat flux or the total heat transfer rate will be related to that, because it's essentially the plumes which are carrying the heat from the surface. So this is, as I said, a very different type of convection flow. And it is again natural convection, but it has some similarities with Rayleigh Bernard, but there are a lot of differences. And essentially it is convection in a tall vertical tube which is open at two ends. And the easiest way to imagine this type of flow is if you have some sort of heater in a still ambient, the hot fluid rises and creates a plume. So now you imagine putting this heated body inside a tube which is open at the top and closed at the bottom. So imagine putting a candle here. So the hot fluid rises, but there is no path for the cold fluid to come from the sides. It has to come from the top. So what happens is you have simultaneously rising hot fluid and falling cold fluid. The falling cold fluid is coming from the ambient, and the rising hot fluid is going from this heated surface. So in this section, for example, simultaneously you have rising fluid and falling fluid, and because it's incompressible flow, equal amounts of hot fluid and cold fluid will be going up and down. So it is zero mean flow situation. And so at any cross section, the net flow is zero. But of course, in our experiments, we use a separate setup. In fact, one of our summer students tried this experiment by putting a candle here. And what do you think will happen? Will extinguish. It will extinguish, why? But oxygen is coming from the top. Because hot air from the candle flame will rise up. To take its place, oxygen-rich ambient fluid will come down. So it turned out when we did the experiment, it was quite, unexpected. So like you said, it will go off after some time. But if the tube length is correct, then it would burn for a while, then it would start flickering, but not go off. Then again, so there was a periodic, it would never go off completely if the height was right. So but of course, if the tube length is higher, then it would extinguish. And if the tube length is shorter, then it won't extinguish because there is enough ambient air coming and feeding the candle. So the way we do the experiment is by having a long vertical tube, have high density fluid at the top, low density fluid at the bottom. So this density difference can be created either using salt, again differences in salt concentration, or by having a heater here and circulating cold fluid at the top. So as I said, you get zero mean flow, and an important thing is that since the tube is tall, you get axially homogeneous turbulence. That is, it's exactly like a pressure-driven pipe flow. At each section, statistically, the flow is exactly same. So it's axially homogeneous, and it is a linear density gradient. Unlike in Rayleigh Bernard convection, where it is almost isothermal, here you get a linear density gradient necessarily because it's a long tube and you're imposing two different densities here. And of course, as I mentioned, you get very high Nusselt and Reynolds numbers. And the turbulent energy production is entirely by buoyancy. So these are some of the references. So this is one setup where you have about a length of about 1.5 meters tall, and two large tanks, and the two ends of the tube are open. So we put fresh water to begin with here and salt water here. There is a stopper which prevents the mixing. So then you remove the stopper, and because this is heavier, so it is an unstable situation. So the heavier fluid starts moving down and the lighter fluid starts moving up. So it's not a steady experiment, but it's a rundown experiment. But the experiment itself takes several hours, so that it's essentially, you can treat each moment in time as quasi-steady. So this is using heat. So we have a heater here, and so one of the advantages with salt is that you get true adiabatic boundary condition because on the walls. Whereas in the case of heat, you need to insulate the side walls. So one has to be careful in how you visualize. And also heat can get lost to the surroundings. So then one has to put a guard heater around here. Then you circulate cold water at the top. So in this case, you get steady convection because whatever heat is generated here is continuously removed from the chilled water at the top. And like I said, you get a linear density gradient. And here you can see that indeed the temperatures are varying linearly. But it is not conduction. Okay? So even though the temperature is varying linearly, the heat flux is due to turbulence. The conductive part will be negligible. So this is a shadowgraph which I described earlier. So you can see that indeed it is axially homogeneous, and this very fine structure is again to two reasons. One, the fact that in turbulence you have very fine structures, but also due to the fact the fine structures are so closely spaced because of the fact that it's an integrated effect. So at any cross section, the fine structures won't be so numerous. And this I'd shown you earlier. Basically, again you see very large gradients. And so here you get a view of the flow in one plane because it's a sheet of light which is illuminating that plane, and so the fluid at the top had this fluorescent dye. So the lighter fluid is actually the heavier fluid. The brighter fluid is the heavier fluid. And this is the particles which you put in the flow, and you can visualize how the particles move around. Again, illuminated with a sheet of laser light. And this is the PIV velocity-vorticity field. So the vorticity is given by the color bar here, and you can see that you get very intense regions of vorticity, which is again characteristic of turbulent flows. And of course, the flow field itself is very random. So you get very high velocities, for example, in this region at this instant of time. And you get all these very random looking vortical structures. And by taking a number of these PIV images, then you can average them out to get the velocity fields. And this is what you get. So of course you use the axial homogeneity to calculate the statistics. So because to get fluctuating velocity field you need a lot of data. So the mean velocity is 0, which as it should be. Both the mean vertical velocity and the mean horizontal velocities are 0. Okay, so there is absolutely no mean flow. Everything is fluctuating flow. And the mean Reynolds shear stress is also 0, which means that mean flow is 0, mean Reynolds shear stress is 0, which means the turbulence production due to shear is 0. So all the production of turbulence is purely due to buoyancy. And so this is the fluctuations in the vertical velocity, and this is the fluctuations in the lateral velocity. This is the center of the pipe. So at the wall, of course, all the fluctuations due to no slip boundary condition have to die down. And the lateral velocity, you can see, go down to 0 much faster because of the kinematic blocking effect of the wall. Whereas the vertical velocities go down much slower because this has to go to 0. And you get a peak here in the vertical velocity fluctuations. Okay, so I think we'll stop here, and it's tea time now? Or? No, I will